Hey everyone, and welcome to today's Explainer. We're jumping right in because we've got a seriously fascinating journey ahead of us. Today, we're figuring out exactly how we measure the invisible, the hidden components lurking in our water, soil, and wastewater. We're literally peeling back the curtain on the incredible, unseen tech that keeps our environment and, well, us, completely safe. So, it all starts with one massive question. How on earth do we measure chemicals we can't even see? I mean, really think about that for a second. You look at a glass of perfectly clear water. Trying to identify what's dissolved in there feels kind of impossible, right? Like pure magic. But as we're going to see today, it's definitely not guesswork. It's structured, brilliant, undeniable science. Okay, let's dive into this. Here's our roadmap for the explainer. First up, seeing the invisible. Then we'll hit light, math, and measurement. Number 3 is the anatomy of a smart photometer. And finally, we'll wrap up with a real-world lab measuring COD. Let's get to it. Section 1, Seeing the Invisible. Now, what's really interesting here is how we actually pull off the trick. The foundational tool we use is the spectrophotometer. It all begins with a totally unremarkable, maybe even boring soil or water sample. But the moment you drop in a specific reagent, boom, it triggers a chemical reaction that develops a very specific color. And here's the absolute genius part. That color's intensity is directly proportional to the hidden substance's concentration. So the darker or more intense the color gets, the more of that invisible chemical is hiding right there in the sample. So we've got our colored sample. How does the machine actually read it? Well, imagine the epic journey of a single photon. Step 1, a UV or visible lamp fires up, producing a broad spectrum of light. Step 2, that light hits a monochromator. Think of this like a bouncer at a club, or a prism. It selects one very specific pure wavelength of light. Step 3, this targeted laser-like beam shoots straight through the cuvette. That's the little glass tube holding our sample. Step 4, on the far side, a photodetector acts like a catcher's mitt, catching whatever light actually makes it through and measuring its exact intensity. Step 5, a microprocessor grabs that raw intensity data and instantly calculates the absorbance. And finally, step 6, it flashes the final concentration right on a digital display. 6 absolutely flawless steps, taking us from a simple light bulb to a highly precise chemical measurement. Moving right along to Section 2, Light, Math, and Measurement. Time to get into the core physics behind the magic. Okay, so how exactly does the microprocessor know what number to spit out on the display? Well, for that, we rely on the Beer-Lambert Law. Now, don't let the name intimidate you. It's actually beautifully simple. A equals epsilon times B times C. This formula is essentially the ultimate decoder ring. It translates how much light was absorbed directly into the exact amount of chemical present. It's mathematical proof that there is a strict, completely reliable straight-line relationship between light absorbance and chemical concentration. So the crucial point is what happens when we compare what goes in versus what comes out. The whole picture just snaps into focus. On one side, we have our incident light. We usually call that I0, entering the sample with full 100% intensity. On the other side, we have our transmitted light, just labeled I, leaving the sample. By measuring the missing light, literally seeing exactly what dropped off between the entrance and the exit, we prove exactly how much was absorbed by those hidden chemicals. It's simple logic. The more chemical in the water, the less light comes out the other side. All right, let's shift gears. Section 3, Anatomy of a Smart Photometer. Let's peel back the casing on the hardware itself. As we move from abstract math into physical hardware, like the Mockery-Nagel nanocolor devices, we've got to talk about the bad guy. Yes, I'm talking about turbidity. It is the unseen antagonist of water analysis. Basically, it's cloudiness. These tiny suspended particles scatter light and can completely sabotage our test results. And the crazy part? It often happens without being visually recognizable to the human eye. It is literally the hidden villain of water analysis. But don't worry, modern devices like the Nanocolor Vis-I2 and UV/Vis-I2 are essentially the heroes of this story. They defeat this interference using an automatic NTU check. This means during every single measurement, the device automatically checks for turbidity and warns you instantly if there's an issue. No more guessing. Plus, they basically operate with smartphone-level intuition. We're talking a massive 10.1-inch HD touchscreen, totally icon-based menu guidance, and, get this, a 2D barcode scanner that automatically recognizes the exact tube test you just inserted. Oh, and with integrated LIMS connectivity, the data just transfers seamlessly straight to your lab's information system. The whole shebang, completely automated. And hey, if we are talking about pure analytical power, we absolutely have to highlight this metric, less than 2 nanometers. Honestly, wow. That is the remarkably small spectral bandwidth on the UV/Vis I2 model. This incredibly tight, hyper-precise beam of light is what allows for the absolute highest precision in your measurements. It guarantees that the specific wavelength you need is exactly what is hitting your sample. It leaves absolutely zero room for error. Let's move to and see how this builds in Section 4, Real-World Lab, Measuring COD. To see all this awesome tech in action, we're going to shadow a tutorial from Mickery Noggle, where their sales manager, Matthias, guides us through testing chemical oxygen demand, or COD. Now, this test is a real game changer. It literally tells us how polluted a sample is by measuring everything inside it that can be oxidized, organic or inorganic. It is absolutely vital for wastewater testing. But as Matthias reassures us with a smile at the end of his demo, water analysis isn't that hard. Well, as long as you have the right tools and follow the proper structure. First things first, though, lab prep. It is absolutely critical. Matthias is quick to emphasize wearing proper safety equipment because, guys, we are dealing with some really strong chemicals here. We've got to ensure our sample pH sits somewhere between 1 and 13. And, this is huge, we must be incredibly vigilant about chloride. High chloride concentrations are completely notorious for causing false results in COD testing. If your chloride is too high, you actually have to dilute your sample before you even think about starting the procedure. Okay, once we're prepped, we dive into the COD 1500 tube test procedure. Honestly, it feels a bit like a high-stakes baking recipe. First, you carefully add exactly 2 milliliters of your sample to the pre-filled reagent tube, close it up tight, and give it a good shake. Then comes the intense part. You place it into a specialized heating block at a scorching 148 degrees Celsius for 2 full hours. Or, hey, 160 degrees for 30 minutes if you're in a rush. Finally, you take it out, let it cool down for 10 minutes, give it another shake to clear any residue off the glass, and let it return to room temp. That's it. The invisible chemistry has officially happened. And this brilliantly illustrates the final payoff. You just wipe that cooled tube clean and simply drop it right into the nanocolor photometer. You don't even have to push a single button. The machine scans the 2D barcode on the tube, automatically pulls up the correct method, runs that crucial NTU check to make sure turbidity isn't messing with us, and boom, it immediately displays the precise concentration of COD in milligrams per liter, right there on that big HD screen. It's almost too easy. Which leaves us with this final thought. The next time you grab a glass of drinking water or walk past a beautifully clean river, ask yourself, what invisible tests kept this safe? It's so easy for us to take clean water for granted, but right behind the scenes there is an entire world of rigorous, unseen chemistry at work. There are dedicated lab techs using brilliant tools like spectrophotometers, harnessing the sheer power of light and math just to ensure our safety. So keep exploring, keep asking questions, and never, ever stop appreciating the incredible science happening right out of sight.